So good afternoon, everyone. Thank you for joining us in the ninth talk of STEMS lecture 2021. Today we have Professor Purvi Gupta from IISc Bangalore with us. Just let me give you a brief introduction about her. She completed her PhD from University of Michigan in 2015, her postdoc from University of Ontario in 2017, and in postdoc in Rutgers University in 2020. Currently, she is an assistant professor at IISc Bangalore. Her research interests are mainly in several complex variables and problems which have connection to convex geometry and harmonic analysis. Today, she will be showing us the role of differential integral calculus in medical science, archaeology, and handwriting recognition. Before we start, just a couple of quick instructions. Please post your questions in the chat box. The moderators are here and we will have a look at the questions regularly and post them at appropriate times or also in the end. Hope you all enjoy this wonderful talk. Over to you, Prof.
All right, thank you for the introduction, Amik. And I actually first want to congratulate Amik and Aniruddin on this excellent organization. It's not an easy task to organize something at this scale online. So very well done.
Thank you.
Thank you all for joining. So when I was first asked to do this, I actually had some other ideas, but then I saw this GIF on the internet and I almost had to talk about it because it raises a very natural question. How do we transmit images, right? Because we transmit images all the time. We send images through WhatsApp, through email. And so, of course, this is a very, very ambitious question. It's too ambitious for a Sunday afternoon. And I am not a computer scientist. I'm a mathematician. So the idea of this talk is to give you a very brief glimpse of the bridge that exists between what you see in the classroom and what people are doing out there. So a lot of objects, the idea is that the mathematics that you will see will look familiar, and that is intentional. So we'll keep things simple, and we'll start first of all with a game of our own. Okay, so we are not going to get into, so let's see if I can find that game for you. So I want to start with this. So what it is, it's a very classical game of solving a jigsaw puzzle. Now I invite you to open your favorite app for a jigsaw puzzle. You can use the website I'm using. It's called imapuzzle.com. Or you can play along with me. I've already done the edges because of course that's the easiest part. But what is the point of this exercise? The point is that when you're solving a jigsaw puzzle, just ask yourself, what process are you using? And I'm going to talk aloud through my process. So when I look at this image, I didn't know what the image was to begin with, but I almost immediately know this is going to be a picture of a cat. I can see two eyes over here. And in fact, that's where I'm going to start with. I'm going to put the eyes next to one another because that's where I expect them to be. What else do I use? So I see some color, some indication of color. So please let me know if you can't see my screen. This is very crucial, otherwise it's no fun. So I sort of match colors. I see there is a gradation. So I see this pinkish region over here, which I expect to match up with the other parts. So let's try this. Excellent. Another pink brown gradation. Very nice. Now I see some fur, which I expect to be at the top of the cat's head. That seems to be the head of the cat. And this allows me also to fit in the eyes, right? So you're sort of getting the point that I am using my understanding of this image. I don't know this full image, but I'm taking certain informed guesses and I'm trying to fit things together. So here, this is not fully fitted in and so on and so forth. So let me do a few more pieces. Let me play around with this idea. And like I see a corner of a furry head. So that should clearly go over there. And let's at least complete the face of this poor cat over here that's being waiting to be completed. So here I go. So I'm not going to do more, like maybe one more brown piece because I can kind of see where it fits in. So it fits in the corner over here. All right, so what did I use over here? I used my understanding of images. I understand what a cat is, what its eyes are. I understand something about background gradation. Now, what if I change the problem and I want to solve this puzzle? So I wipe out the image. I have no image. I have only this puzzle. What am I going to use? So I have not even done the edges, although of course they're easier to do. Now, what am I going to use to put this puzzle together? What is the only option I have left to me? By the way, please feel free to interrupt. This is really about a conversation. I don't want to go on and on for this 1 hour. So please interrupt, feel free to ask questions or give comments. So I want to know what you think what is the only thing one can use over here to put this puzzle together. I'm going to start dragging some pieces around.
Ma'am, there are some comments in the chat box saying maybe we can try using color gradients or connecting points.
So I'm not sure what that means. So can you elaborate?
Like they're saying maybe we can start with putting the boundaries first and then we can go on.
Okay, good. So that's exactly. So we kind of understand, very good. So we understand that, okay, the edges are, of course, the places to start. So I already have two pieces fitting in like this. I recognize a corner piece over here, which also fits in well. And so, of course, it seems kind of natural to begin at the corners. And then with the intermediate pieces, what we really have, so even though you may be seeing some variation on the screen, imagine that this is a completely white image. So I have nothing to go by. And what I really have left with me is how these borders fit into one another. So one really has to rely on the shape of the borders of these images. And so you may ask me at this stage, why would I even want to solve a puzzle like this? Why would I want to solve a puzzle without a picture? And my answer is that, well, what if you were trying to make a computer solve a jigsaw puzzle? Now, it may not be a very sophisticated computer. It may not have a sense. So even if the jigsaw puzzle has an image, the computer may not have the sophisticated sense of what are eyes, what is a cat, what is the sky. So it may have a very coarse understanding of what shapes are, and what it might try to do is it might try to fit in the shapes. So this is to somewhat convince you that maybe just understanding boundaries is an important problem. So we try to fit in, and here I see that I'm not able to fit these two pieces in, because even though from afar it looks like the shapes should fit into the above shape, it doesn't exactly do so. Okay, so now at this stage, you should have another question, which is that why would we even want a computer to solve jigsaw puzzles? And the point is, what if these were not pieces of a puzzle? What if these were fragments of a bone? So let's say you have found some bone fragments at an archaeological site, but they are very delicate. So the archaeologist, she doesn't allow you to touch them. She promises to send you images, and you can use your computer to try and reconstruct the creature whose bones you have found. And that is actually used. I mean, what if these were not pieces of a jigsaw puzzle, but they were maybe shredded pieces of an important document that you have found? And once again, you want to use images to put them together. So hopefully this kind of tells you that this game that we have come up with, which is to solve a pictorial, so imageless jigsaw puzzles, it can have applications, and it is in fact used. So we have to come up with good algorithms to do this. Okay, so let me pause and see if there are any comments or questions before I move on to the next idea. So so for me, it's hard to track the chat box. Please keep me updated if there are any comments or questions.
Yes, sure, ma'am.
Thank you. All right, so now we want to start talking about shapes, and what we want to do is we want to give them more precise meaning. For that, what is important is a point of view. So let us come to that. So here I have taken an image. This is from my office. This is a coaster that I use to keep my coffee mug. And I have taken this image from above my table, and I'm going to roughly assume it's a square. Okay, it's a squarish shape. This is the most square item I could find in my office. And here's the thing I'm going to do. Imagine that I'm viewing this from above, or rather this is an image from a camera which is on the ceiling, and it's capturing images on my table. And of course, on a daily basis, I move this thing around, and let's say the next day, this is the image it captures. So roughly this is what it looks like. So what is this object, right? This is still a square, but we have done something to the square. What have we done to the square? Okay, I'm going to keep filling in the silences, but if anybody wants to speak up, go ahead.
We have rotated the leg square.
Good, very good. So we've rotated it. We've also slightly translated it, but it's still essentially a square. And now what happens is the auto zoom on my camera starts working up. So the next day I find an image like this. So now what it has done is it's scaled up the square. So, but still, it's still a square, good enough. Now I need to move my camera. If I move my camera, the next day I get an image like this. What is this shape now over here? So I have lost something. In this process of moving my camera, I have lost this property that the object I'm looking for looks like a square. Thankfully, some things are still there. You know, parallel lines are still going to parallel lines. I've probably lost the angles over here. All right, so this is still okay. You're still in okay familiar ground. But then what if my camera moves closer? I then get an image like this. Now this, if you look at it carefully, you've lost almost everything. So angles are gone, lengths are gone, and things that were parallel are no longer parallel. Right? So if I now put all these images together and give it to my computer and say, can you please find the poster for me? I can't just tell it to look for square shapes because these are not all squares. So how do I communicate with the computer? And you may, of course, also say that why go through so much trouble? Why not fix the position of your camera and take one fixed point of view? And this is done. People do fix their cameras, and we will, in fact, go into that territory later on. But I want to mention that we can't completely ignore the kind of distortions we are seeing over here. So let me pause, and before I convince you that these distortions are important, let me see if there are any comments or questions.
Ma'am, so just now you said that like we can fix the position of camera. Like it may not be always possible to fix the position of camera, right? Like it can vary. So in that case, we can't do that.
Absolutely. So you're absolutely right, because we can't always define the conditions of the problem. Sometimes, I'll sort of come to that. So we can't. Certain situations, like when we were solving the jigsaw puzzle, we can assume that we are looking at the puzzle from above and maybe say, okay, everything is up to rotation and translation. So you see the pieces lying about, and all you've done is rotated and translated them. But yes, and so just to your point, let's say that we are doing the following game, which is we are taking pictures with a camera and we want to take a panoramic image. What does your cell phone or your camera do? It takes certain individual photos and it tries to stitch them together. And here are two images, right? So this is exactly what's going to happen. Now a distortion has happened in the second image, which you just cannot help. That is the whole point of taking a panoramic image. So how is this distortion going to, how are you going to stitch this together? We are going to identify a shape. So I have decided to identify the frames of these doors. I somehow am able to convince the computer that these are the same objects. So based on this, the computer figures out what is the extent of distortion needed and then puts these two pictures together. So the kind of distortion we mentioned towards the end, that is really something that we have to take into account. So let me now put all of this in a table. Let's organize our thoughts. And then this is also my excuse to introduce certain mathematical terms to you. The goal is not to intimidate you. It is to set the language for what we are going to do ahead. Okay, so let me explain this table to you. On the leftmost column are pictures that you have already seen. Think of them as examples. Now, in each row represents our definition of a shape. So in any row, I will think of two shapes as the same as long as they differ by certain allowable translations. And I have told you in the third column what those allowable transformations are. Now, for example, in the first row, I will allow translations and rotations. So a rotated square is still a square for me. In the fourth row, I'm trying to keep track of certain things that remain stable under these transformations. This is not a complete list, but it's a very useful list. And please feel free, or if you want to stop thinking about what I'm talking and just play around with what's on this table, feel free to add other things to that particular column. You may observe other things that remain invariant. There is the second column, and that's important. The point is that when I say what is allowed, I'm allowing a certain group of transformations, or I'm allowing a certain geometry. And what I have in the second column are the names of these geometries. So to start with, the rigid geometry or Euclidean geometry is when we only allow translations and rotations. This is by and large great because lines are still lines. Things that intersect still intersect. Lengths of line segments remain the same. Angles remain the same, and things that are parallel remain the same. Then to this, so by the way, things like lengths of line segments and angles between two lines, these are sometimes known as joint invariants because you need a certain number of points to define them. So for lengths, you need 2 points to define the length of a line segment. For an angle, you need 3 points. That is something to keep in mind. We'll come back to that. Now, if to these transformations, I allow scaling, like zooming in, those are known as similarities. Everything remains the same, except of course, we lose lengths. Lengths do not, they scale up or down. All right, then we go into this territory where we are actually losing more things. So these are known as affine transformations. Here you are allowed to scale in different directions, in different vertical and horizontal directions. You're allowed to scale in different ways, and you're also allowed certain shearing actions. So we saw an example of this, and this, things start getting murkier because now things like lengths, angles, they are not preserved. Lines are still preserved. When two lines intersect, then after these transformations, they continue to intersect. If lines are parallel to begin with, they continue to remain parallel. Okay, so one has to wonder what's going on over here. And the last group, which is really the largest, we are being very generous over here. We are allowing what are known as projective transformations. It seems like all hope is lost in terms of what is preserved, but this is important. And a good way to think about projective transformations is in its name. So imagine you have a three-dimensional object in space, and the only way you can look at it is you can look at its projections onto two-dimensional planes. You get to see all those images, and any two such two-dimensional projections differ from one another by a projective transformation. That's roughly the idea of projective transformations. Okay, so it seems like we have nothing to work with, but there are more developed constants. So there are more developed measurements that one can talk about. So cross ratio is one of them, but this is a term I just want to leave you with. We are not going to define it, but it's something if you come across later in life, you kind of understand the relevance of. Okay, so before we focus on, I want to start talking about some math. So before we do that, let me also mention that sometimes when you work with a group of transformations, you allow yourself a certain subgroup. So here within affine transformations, we can look at those which are area preserving. So what I'm doing is I'm almost artificially introducing an invariant. And what Euclidean is to similarity, equiaffine is to affine. So affine is just a scaling of the equiaffine situation. And if I have time at the end of this talk, we will maybe talk about equiaffine geometry. So what am I going to talk about? My goal is to take curves, which I view as borders or boundaries of regions or shapes. I want to assign certain measurements to them that first of all don't change if I do certain allowable transformations. Secondly, if you give me those list of measurements, then I should not have two different curves corresponding to them. I should have only one. It should uniquely determine a curve up to these transformations. And the third problem, which I'm not going to go into a lot, is that, okay, we are talking from the point of view of application. So it's not enough to know that if you give me a list of measurements, then there is a curve. That's not good enough. I need you to give me a recipe for constructing that curve. Sometimes we want to reconstruct curves. So that is the third aspect of this problem. So I want to tell you how we can use these, the fourth column, these small things that we have observed. How can we use these to cook up such measurements? And I am going to do this in the Euclidean setting for the following two reasons. One, that there are lots of objects here that are familiar to you. So I want you to see those. And two, this is sort of the easier setting. And, this being a Sunday afternoon, I want to do the easy part and I want to leave the difficult part for you as an exercise. Okay, so please think about the process and not so much about the formulas over here. Okay, so at this stage, let me pause again. Let me see if there are any questions, any comments. If you're unclear about what we're going to do, feel free to ask.
Just one question here. So are we dealing only with plane, the two dimensions, or are we going to?
No, so for this talk, we are only going to talk about two-dimensional shapes. And so therefore, I'm restricting to curves which are in the plane.
Okay.
Thank you. So that it already has lots of applications. And of course, I'm thinking of this mostly in terms of like camera images. So that's why I have this left-hand side as a guide principle. All right, so what I'm going to do at this stage, I'm actually going to switch to my tablet, and that's where we are going to do the math. I hope everybody can see it. I'm going to disconnect my keypad so I can write on this. And at any point of time, if you cannot see what I'm writing, please feel free to interrupt. Okay. So what we are going to begin with, and again, do think about how we can take this to the affine setting and things like that. So let's start with the foundation. The foundation of anything like this is a good parameterization. A good point of view. I mean, in some sense, how do we describe the curve? And what I'm going to use for this is the first joint invariant. So I mentioned this word joint invariant. And in my list for Euclidean or rigid transformations, I mentioned that if you give me 2 points, then I have a way, I know that the length of the line segment remains unchanged by these allowable transformations. So now I'm sure many of you can tell me, how can I use the length of line segments to talk about the length of a curve? What is the idea over here? So let's just say it's the length of AB. So here's an idea that you would have definitely seen, hopefully seen in calculus. And again, my focus is really on, approximation schemes. Remember, we are trying to see how we can get this information if we just have certain data points on this curve. So what I do is I select certain points. So let's call this P0. Let's call this Pn. And now let's say I have certain points on this curve, P1, P2, and so on. And what I do is I kind of take this polygonal path. So it's a piecewise linear path. I'm just attaching or joining consecutive points with line segments, because all I know is I know lengths of line segments. That's all the information I know how to compute. So let me give some names. So P is going to be the polygonal path, which I call P0, P1, all the way up to Pn. And then I know how to compute the length of this path, right? Because all I need to do is I need to add the length of these individual pieces. They're all straight lines. And there's one more thing that I'll put in here, which is that I have, of course, in the beginning, I just chose these points somewhat randomly on the curve. And of course, you have to make certain observations in that if you did want to add other points in between, then how does it affect this computation that I'm doing, right? So does it improve it? Does it increase it? Things like that. But I also want to talk about, I want to mention this object, which is sort of telling you something about this, how I've chosen these points. And it is the length of the maximum length of the line segments that make up this particular polygonal path. So let's say 0 between j and n minus 1. We're only going up to n. Okay, so because I believe that this is stuff that you may have seen, so here's something that we know, that when the curve is nice, and again, refraining from getting too technical over here, when the curve is nice, we can define the length, and I'll just say length Euclidean of this curve, which I'll call capital gamma. The length is, I look at all these possible polygonal paths and I look at the least upper bound. So when the curve is nice, this is a finite, well-defined quantity, and I can call that the length of this curve. Okay. Now, from the point of view of what we are talking about, let's put some things down. So this is a global measurement. I'm telling you the length of the full curve from the start to the end. And it is invariant under rigid transformations because the very foundation, the very basic object that I use to construct it is invariant under rigid transformations. So my construction takes that into account. Okay, so far this is just a global object. I want to say something to connect this with what you would have seen. So let's say that we have a parameterization for a curve. So what is a parameterization? It is just a way of describing a particle that is moving along the curve. So suppose I have a certain parameterization. So let's say this is the position of a particle on gamma at time t. And there are two assumptions. I'll not write these down. There are two assumptions. One is that you do start at the beginning of the curve and you end at the end. And the second is that you're always moving forward. So you are allowed to stop, but you're never allowed to turn back. So that's the kind of parameterization I'm talking about. This is a parameterization. And then in calculus, you would have seen that the object that we have just defined, you can actually give a formula for it. So let's say that t is the total amount of time it has taken the particle to reach the end. And so what do? You do x prime t square. So you look at the speed of this particle, dt, and this is your length of this curve. You can use your parameterization to compute that. Okay, now if, and this is this foundational thing of setting a good parameterization, if your speed, so let's write it like this, if the speed of the particle is 1 unit, we call gamma t parameterization by arc length. And I'm sure some of you would have come across this phrase, parameterization by arc length. And I'm going to call it S of t. This is going to pop up later, but I just want to mention one significance of this from the point of view of what we have been discussing. So let's say that you're standing on the, so okay, what does S of t represent? S of t represents that point on the curve that is t distance away from where you started along the curve. Now, from the point of view of what we are saying, right, things have to be invariant. Let's say you're standing on the curve somewhere, and you want your friend is at the start point of the curve, and you want your friend to come and meet you. And your friend has an image of this curve, maybe on her cell phone or something, but she has some sort of rotated or translated image. Then what is a good way to tell her where to come, right? Because your coordinate system might be different from her coordinate system. So what is a good way to tell her where to meet you? Well, you say, why don't you walk t distance from where you are, and I'll meet you there. So this is a way of referring to a point while standing on the curve. So that's why it's a useful object from the point of view of what we are trying to do. Now, let me mention an aside over here before we come back to the issue of assigning certain measurements. So let me pause and see if there are any comments at this stage.
Ma'am, there is a doubt regarding what is a global measurement.
Okay. So what this is very good question, because this is important. So by global, I mean that I'm assigning a certain measurement to this full curve right now when I define the length of the full curve. So I'm not really standing at a point and just assigning a number to that point right now. Right now, I'm just talking about the full length of this curve. I hope that answers the question.
Yes, ma'am.
All right. Thank you. So, right, that's the important part, and we will come to that. So thank you for that question. So, okay, let me do the following. So let me mention a brief aside over here. Another question?
Yeah, so I had a question about the way you define the length. So, what if the curve is parameterized in such a way that you go forward and then again come backward and then again go forward, so that the picture seems to be the same, but the curve is retraced. So, will the length have like double segments be counted in the length?
Absolutely. So that's why I impose these. So if I want to really talk about the length of the image, so of course there is one thing about how much distance the particle has traveled, and what you are describing to me is the how much distance the particle has traveled. Whereas from our point of view, we are interested in the length of the curve that we are viewing on the plane. So that is why I have imposed the condition. If I don't impose that condition, then we have to keep track of translations, because the definition doesn't take that into account, unfortunately. So we have to do some sort of sign distance in that case.
Right. Okay.
Okay. So very good point. So this part parameterization is special, not keeping the particle in mind, but keeping the path in mind. Any other questions or comments? Let me shrink this a little bit so you can see what's going on over here. Okay, so I did want to, before we move on to what do we do with such a measurement and is it good enough for anything that we want to do, let me mention an aside over here. And for this, I want to use a slightly different curve. So think of this as a piece of the x-axis and think of this as the curve y is equal to, graph of the curve y is equal to x squared. And let me take 4 points. So let's say that information has come to me in the form of the following 4 points on this graph. And I have P1, P2, P3, and P4. By the way, this is an example of a curve where you can actually, that supremum is finite. So this is a nice curve from our point of view. Okay, now if you want to go and do these computations later on, let me also give you some coordinates so you can actually compute certain distances. So my coordinates are going to look something like this. And here n is just some fixed natural number, okay, is a natural number. So as n gets larger, I'm actually focusing more and more towards the origin. But I'm really just giving you these numbers if you want to check what I'm saying. And then let's say P4 is 1 over n squared, 1 over n to the 4. You can take your favorite n over here, preferably greater than 1. Okay, so what's the point? So what we just saw, so let's look at the polygonal path, which is, I'll draw this in green, which is you connect P1 to P2, you connect P2 to P3, and you connect P3 to P4. So my P is the polygonal path P1, P2, P3, P4. And if this is the only data I have, then I know that the length of the curve, the best thing I can say about the length of this curve, this is my best approximation. It is the length of this polygonal path. So let's say I don't know anything about the path. So let me get rid of the path itself. And I only have these 4 points. Then this is the best I can say. Now, let's say that the data comes to you in a way where you don't even know the ordering of these numbers. So at least I knew that P1, P2 came after P3, P2 came after P1 on the curve and so on. Now I don't have an ordering, okay? So now, so what I have over here, let's call this a polygon, sorry, let me use a different color. So this is a polygonal reconstruction. And so this is a little bit about how do you reconstruct curves if you only have data points. And let me suggest a new path, okay, which is, and I'll tell you where this is coming from. I'll use a different color. I join this point to this point. I join this point to this point, and then I go like this. So this pink path, so now I don't have any labeling, okay? So I can't write down what the path is, but my claim is that this is what is sometimes known as the traveling salesman path. In that, so this is a very old observation. This goes back to Menger, the mathematician. This was from the 30s. So his point was that let's say you have a collection of points, they lie on a curve. You don't know the order in which they lie on the curve, but you want to say something about the arc length. Then what do? Try to take the most efficient path, polygonal path. The efficient polygonal path is that, so this is the, this is a famous traveling salesman problem. Let's say these four points are cities. You want to visit each city exactly once, and you want to take the shortest path. So P prime in this picture with these coordinates represents that path. And you can clearly see that P and P prime are not the same. Menger's point was that if you increase your data set, so if you keep increasing your data set, then you can also use traveling salesman paths to compute the arc length of the curve. Those also do a good enough job. This is for length, but if you actually want to reconstruct the entire curve itself, does that also work? So this is a good question to think about. So people have done some work on this. So maybe let me write it more clearly and then pause for questions. So do traveling salesman paths also do a good job of reconstructing the paths? Because if you look at the pink picture, already it seems like we have gone off the path quite a bit. So we are not just interested in its length, we are trying to recover the full path itself. Okay, so this was an aside, but I thought it was interesting. So I want to see if there are any comments or questions. Anything at all? It's a good time to ask.
So then there is a question in the chat box. Doesn't the traveling salesman path might lead to retracing your path?
Very good point. So in fact, people did think that the way Menger proved his result, maybe the point was that after a while, P prime just becomes P. Like if you take dense enough points or enough number of points, then ultimately there is no difference between P and P prime. So you end up getting the same curve. But the picture that I gave you right at the beginning, so that curve looked a bit like that. Let's see if I can actually get back the curve. And I gave you certain coordinates. So now what you can do is you can actually take some more points. So you can take this curve all the way to 1 and you can add certain other points, but keep these 4 points fixed. Then no matter how large your n is, you will keep getting that p is not equal to p prime, and the length of p prime will be smaller than p. So there are some results where you have to impose more conditions, and then p prime, the traveling salesman path, does in fact retrace the original curve. And one of the conditions that you need to get is that, first of all, you have tangents in both directions. So you have tangent spaces. So let's say you're at a point, you have a well-defined left and right tangent. More importantly, the angle between the tangent should be less than 180 degrees. So here what's happening is, here in this picture, when I come, I get a tangent in this direction, and then the right one is sort of going like this. So this is exactly 180 degrees. And this cusp-like situation is when you will not have a retracing of the curve. You may not have a retracing of a curve with traveling salesman paths. But if you impose a condition on the angle, then yes, these traveling salesman paths will reconstruct the curve as well later on, as n becomes large. Does that help?
Yes, ma'am. Thank you.
All right, thank you. All right, so let's get back on track, which is that we wanted to talk about how can we assign measurements. So far we have just talked about lengths of curves. And obviously this is already a problem, right? Because I can easily give you two shapes which have the same total length, and they're not the same shapes even after rotation and translation. So what are some adjectives I can use over here to differentiate between these two shapes? Like, what are some ways you can describe these differences? Any suggestions? Any adjectives?
There are comments, maybe it can be area.
It can be area, very good, but I can also, okay, so very good point. So area is a good thing to think about. Anything to do with the shape. So I want to actually focus on the curves. So let's say we don't have such a good sense of the inside part. Based on the properties of the curve, can I have some other adjectives here? So focusing on the shape aspect of the two things. So how can you differentiate the right-hand side from the left-hand side?
Ma'am, there's another comment, maybe concavity and convexity you can use.
Okay, good. So yes, it does seem like they're sort of bending the same way, but maybe one thing is that this picture should seem a little flatter to you, right? So this seems a little more round. So let me write these ideas down: concavity, convexity, because these are things that we can try to measure along the curve. And one way to think about it, it looks like I've taken this circle and I've flattened it up a bit. So this is what I want to use as an idea. And this brings me to my second joint invariant in this entire geometry, which is angles. By the way, this does connect to the idea of areas. So whoever said, let's look at areas, I have decided to take the approach of angles because it was listed in it was there in my list, but one can also approach this using areas over here. So, so in my list, instead of angles, if I had written area, then I would have gone in that direction. And so for an area, we need 3 points, A, B, and C. And I'm going to use the fact that this is an invariant. The angle between two lines like this is an invariant object.
Ma'am, there are also some other comments. Maybe you can use eccentricity of the curve or perimeter or slopes at different points.
Okay, eccentricity, slopes, very good. And so eccentricity is, of course, assuming a certain shape. So here I have drawn an ellipse kind of thing, but then I could have something of the same length, which would be, more like an amoeba over here. And then, this becomes a little harder to describe. But yes, so what you're telling me, these are somehow point-wise features. This is bringing me from global to local numbers. So maybe something I can say about points.
Ma'am, also curvature is one of the comments. Curvature is also.
Right, very good. So I think that hopefully some of this that I am very good. So curvature. So we see that this is somehow captured in this idea of round and flatten. Those are exactly the words that I had mentioned earlier, and you're absolutely right. So these are all things that now we are sort of, instead of looking at this global property, so perimeter has to do with, of course, the length, Now we are looking at pointwise property and trying to track that. Very good. Okay, so let's focus on this. So let's take this angle, and it's something to do, all of these are something to do with the fact that how the curve is turning. Maybe not so much the area idea, but all of them are saying how the curve is turning. Right, this is what we want to capture. And here is my idea using the fact that I have some notion of an angle. So maybe let me try the following idea and see where it leads. So let's go back to our curve. And I'm deliberately drawing nice curves with no corners in them. And I focus on a point and I want to say something about how this curve is turning at this point. And I don't want to use, so why I'm sort of ignoring some of your comments about slopes and all is actually I don't want, let's say I don't have calculus at my disposal. What I have is I have these very basic objects. I have lengths, I have angles, I have some amount of trigonometry. Let's say I don't yet know how to compute derivatives. So then I'm going to just fool around with what I have and I'm going to try and come up with the following recipe. Okay, and you can of course try to take a different recipe. So for example, let's say that I take, so P is my focus point. I take 2 points near P, A and B, and I'm going to focus on this angle over here. For those of you who are thinking of area, I would also recommend to do the same exercise where instead of looking at the angle, look at the area. This is an alternate suggestion. Look at the area and do exactly what I'm doing and see where you go with that. Hopefully you land somewhere, in the vicinity, in the ballpark of where I land. Okay, so here's my recipe. I want to define some quantity. It's just an idea. And the idea is that I want to define a notion of an angle of a curve at a point. That's why it's in quotes. And I look at this angle, APB. And I don't know if this limit exists. I don't know what will happen, but I drag A towards P and I drag B towards P. Okay, this is just an idea. Maybe I'll get a limit. And if that limit is well defined, let me call that the angle of this curve at that point. So let me pause and see if there are any questions at this stage, what we have done. Okay, so very good. So now again, so if you're thinking about area, you can try to do this with areas as well. You can also try to see that if you did know how to compute derivatives at this point, how would this relate with the slope at this point? What would you be able to say with the slope? But by slope, I mean, you of course know we have assumed that there is a tangent line over here. How would this be connected to the slope of that line? All right, so let's do the following. I actually want to do a sample case. So I want to try this idea out and I want to try this for a circle, which is a good enough shape from our point of view. And when I try this for a circle, I want to see what do I get. So let me put a line underneath. And let me give an equation for this circle. So I've deliberately shifted, I want to take a circle of radius 1, but I have sort of shifted it. It's not centered at the origin. I've shifted it above a little bit. So I have 0, 1 as the center of this circle. And P is going to be my point. And I'm going to try and do this. And let me take a different color so that we can focus on the angle. And have deliberately chosen these points to be equidistant from, at least in the x direction, they are both delta distance away. So I do minus delta and delta over here. Okay, and this is my angle over here, theta. Let's call it theta. Let me also connect these 2 points and see what is going to happen. So by the way, you can solve for this height and you'll get 1 minus square root of 1 minus delta square, because you do have the equation of this line, of this curve. Okay, so instead of directly trying to figure out what theta is, I'm actually going to try to understand what sine theta is. So let me now erase the underlying curve. Let's forget that for a bit. And let's just focus on what we have over here, the angle I have over here. So let me expand this a little bit so that you can see clearly. And remember, this angle is pi over 2 minus theta over 2. So I'm going to use some, usual trigonometry tricks. And I'm going to go ahead and compute this quantity. Remember, this theta depends on delta. And my goal is to take A and B going towards P. So delta is going to go to 0. That's the goal. Okay, so let's compute this. Now this is nothing but 2 sine pi over 2 minus theta over 2 cos pi over 2 minus theta over 2. Now we have a triangle, we have a right angle triangle over here. So my sine is, sine of this angle is 1 minus square root of 1 minus delta square divided by the length of the hypotenuse, which I'll just call h right now. We'll plug that in later. And then for cos, I use this, I have delta over h. Now what is h? How can I figure out h? What I really need is h square. So what is the thing that I can use for h square? So here's my triangle. One side is delta and one is 1 minus square root of 1 minus delta square. I hope I'm still connected.
Yes, ma'am.
Okay. So all we are doing is we are just using the Pythagoras theorem. And we are just going to use this over here. So, okay, so do this computation. It's a simple computation. And the idea is, I want to see what happens to this as delta goes to 0. So in the denominator, you're going to get 2, 1 minus square root of 1 minus delta square. Okay. And so in the end, this is just going to be delta when things cancel. And this is going to go to 0 as delta goes to 0. So as you bring the points A and B along the circle towards P, sine theta is going to 0. Okay. And we have some guesses on what theta can be. So, okay, my first observation is sine theta is going to 0, but we have to be a little bit more careful. So let's draw our picture here again. And this should tell us something about where theta is going. So what are my choices for theta over here? And I think the best way to check this is to actually compute the cosine. I think that's the best way to tell us so theta could of course be 0 or it could be pi in this situation. And I'm not going to do this computation again because I mean, we've done, all the components are there for you to do this computation. You'll find that cos theta actually goes to -1 as delta goes to 0. So if I put this together, my recipe that I had, my A, this angle at this point P for this circle turns out to be pi. So let me just say this over here, whatever this limiting angle was, it turns out to be pi. Okay, let me see if there are any comments over here at this stage.
There's just one question here. So is it true that there is it'll always be a 0 or pi, or can you give an example where it's not a straight line?
Very good, very good. So this is it. You have basically gotten to the crux of the matter that if the curve is nice, I am getting, at least in this picture, I'm getting pi, okay, you have recognized that because we would get the same thing if we did a straight line, right? So would get this for a straight line as well. And my answer is that as long as you have a tangent, if you have a nice curve over there, it is smooth over there, you will keep getting pi, which is very unsatisfactory because our goal was to be able to separate the circle from a line at least, right? Because the circle and a line don't differ by a rotation and translation. So yes, this is disappointing. And your question is right. Smooth points, you would always get pi.
Okay, thank you.
Very good. So now the point is that whatever my recipe, my idea was, it seems to be failing. But now this is the process I want you to focus on. So in mathematics, you don't give up because you have an intuition and you go with it. And here the idea is what does calculus tell us to do? Calculus tells us not to focus on final answers. It tells us something about thinking about rates, right? So you're going to pi. How are you going to pi? That's important.
A
So
good suggestion from the chat box. We can look at the second derivatives maybe.
Very good. So we are actually heading precisely in that direction. So you're right that what we have done is we seem to be looking at linear information only. And so we need to look at second derivative. And I'm going to tell you a way to do that, just looking at these kind of things we are playing around. So very good suggestion. And because then that's clearly the difference between the circle and the line, right? So my point is that even with what your initial idea was, we focus on sine theta, which I saw was delta, and as it was going to 0, so let's bring this picture down here. Let me copy this. Okay, so with this picture in mind, what I saw was that sine theta was behaving like delta. And if I look at the length of AB, that's actually 2 delta. Okay, so I'm going to divide by 2 delta. I'm going to multiply so that everything becomes 1 as delta goes to 0. Now, this is my new object of study, and this is not a coincidence. What we are looking at, so first of all, we are getting 1 because this is 1 divided by the radius of this circle, which was exactly 1 radius of circle. We started with the radius 1 circle. In general, if you have a triangle, APB, this was theta, then 2 sine theta divided by the length of the opposite side is exactly 1 over the circumradius. This is an exercise for you to think about circumradius of this triangle APB. So by playing around with this, instead of looking at angles, what we should have done was we should have looked at circles over there. So this is my new idea based on what we just saw. And which is that in this curve that I have, let me make it look more like the curve we had earlier. We do take these 3 points. And again, if you're wondering why I'm avoiding derivatives, why I'm constantly, even though all your comments are very good, the reason is that once again, when we are trying to make a computer compute these things, we may not have the full parameterization of the curve. We may only have data points. So we may have P, A, B. Maybe we are allowed to collect more data. And therefore, I'm focusing on numerical schemes more than actually calculus methods, but I will give a formula. So my new idea is that I define this quantity kappa, and some of you will recognize this letter. What this is, and again, one has to justify this limit exists, but it is 1 over the circumradius of APB, this triangle, as A is pulled towards P and B is pulled towards P. So I look at this very badly drawn circumradius. So let me make circumcircle. So maybe this does a better job. Okay. Okay. And this is precisely the curvature. And let me put in the word Euclidean curvature, because the way we have constructed it, we have only used angles and we have used lengths, and we have already observed that angles and lengths of line segments are Euclidean invariants. So keeping that in mind, what we have constructed is not affected by rotations and translation. So this is a good way to track certain changes that are happening along your curves. Okay, so if you had gone down the path of areas, you would have also reached the same point. You would have also come up with this idea of a curvature. And at this stage, let me actually connect this to what some of you have already been hinting at, that if gamma t is xt yt. So let's say now you're not feeding this into a computer, but you want to compute this by hand, and you know enough calculus, then kappa at the point gamma t has a very simple recipe. You look at first derivatives and you treat that as a vector. You look at second derivatives. Of course, I'm assuming all these derivatives exist. You take the determinant of this matrix, and then you have to normalize this with the length of this, or what I was calling speed earlier. Let me write this correctly. 3 over 2. Okay. This would be the recipe in terms of actual derivatives. So the various suggestions that were raised, look at first derivative, look at second derivative, look at concavity, convexity. They're sort of captured by this particular object. But the main difference is that I have not come to this using calculus. I have come to this using these very basic joint invariants. Now, before I pause for questions, let me mention that there are two things I want to mention. First of all, these are known as differential invariants for very obvious reasons. You're using derivatives to define them. Secondly, it's a local invariant. It is defined at each point. It's not a property of the full curve. You can focus on a piece of a curve and compute the curvature there. There's another point I want to make. It is often useful to view this curvature as a function of arc length, because remember, arc length is a very good way. Arc length parameterization is an invariant way to look at curves. So sometimes you will often see them write kappa of S, which is the curvature at the point which is S distance away from the starting point along the curve. So this is often a good way to describe this curve. So let me pause and see if there are any questions at this stage before we say something more about curvature. Oops, sorry.
One question here. So what is the motivation behind defining kappa of gamma of t that way?
Okay. So this is basically coming from, you mean directly in terms of these derivatives?
No, like what is the matrix that we are taking the determinant of, and like how do I see things moving around here?
Very nice. So here what's happening is that you think of gamma prime t as a vector. You think of gamma prime prime t as another vector. And what you are looking at is you're looking at some sort of an area, this determinant. Right? And so when the curve turns, the relationship between the rate at which gamma prime is changes. So at some points you could get a parallelogram that looks like this. And at some points it could look like this. So of course the area gets affected. And that is exactly capturing the rate of change of gamma prime, which is being captured by gamma prime over here. That's what this determinant captures. It captures this particular area. Does that help?
Oh, yes, thank you.
Yeah. Okay, so this is determinant of gamma prime t, gamma prime t. All right, so now what did we want to say? Yes. Any other questions? Any other comments or suggestions at this stage for what we are doing here?
No, I think I guess we'll take it towards the end maybe.
Okay, sure. Okay. So let me say the following, that we had this question that can we completely, if we measure a curve, can we completely determine the curve from that measurement? And this is a very standard fact that if you know the length of the curve L and you know this function kappa as a function, not just, so here remember for each point we have a kappa. This completely determines a curve up to rotations and translations. Of course, I'm assuming something nice. If you notice that my calculus definition for kappa required two derivatives. So this is in fact this actually somewhat answers a question that knowing L and kappa really tells you everything about the curve. This is the first fact. But the second fact is, this is more of an observation than a fact. Remember, we mentioned the fact that capital L is a global property. It's the global length of a curve. And sometimes we don't have a handle, like we don't have the full image of a curve. As I said, we might just have certain data points on the curve. And if we have certain data points on the curve, then there is something that people study when they want to understand curves. There is a related object that they look at, which is known as the signature of a curve. This is a new curve. And what it does is it takes the point T to kappa of t. So you have some parameterization to start with of the curve. T. Now you look at this new curve where t is going to kappa of t, and I'll tell you what kappa s of t is. Kappa s of t is rate of change of curvature with respect to arc length. So this is a measurement that is lying along the curve. You're not using any coordinate axis to understand this. You're really sitting along the curve and trying to figure out the rate of change of curvature. This gives you a new curve. If you look at a circle, so by what we discussed earlier, the circle will always have curvature 1 over r, if r is the radius. So for a curve, for a circle, so let me write this down. This curve, this new curve, signature curve, is always just a point. Because the first term is a constant, the curvature is constant. So there is no rate of change of curvature. The curvature never changes. So this is just a point which is 1 over r comma 0. So this is a good, if you can get curvature signature, if you can get these signature curves, then this is a good indication that the closer your circle, or sorry, the closer your curve is to a circle, the more concentrated this new curve is about a point. So you can detect circularity by looking at this signature curve, which you can have some numerical schemes to compute with if you have data points. Another thing is that symmetry of the curve. So remember, the circle is very symmetric. You can keep rotating it and you'll still keep getting the same circle. Symmetry gives you winding of this new curve. So if you have some sort of threefold symmetry, then this signature curve kind of winds around itself 3 times. Circle has sort of full symmetry. So that's why you're just basically just standing at a point. It's like just repeating that point over and over and over again. So this is something that is actually used more than the length and the curvature function, although theoretically they do completely determine a curve. And there are, and this new signature also completely determines certain, and I have to put in these certain every time because every result comes with conditions, certain curves, up to rigid transformations. Okay, so let me pause. I want to actually, even though it seems like we have completed the Euclidean story by giving you complete measurements that determine a curve, and of course you can ask me questions at this stage. Can you reconstruct the curve given a signature curve? There are many questions of that kind. There is something more to be said about this story. Before I get there, let me see if there are any comments or questions.
There was one interesting question on generalization saying, can I generalize to a curve sitting in R cube, or can we talk about, say, a surface in R cube? So what will stay the same and what will change?
Very good. So of course the process, so yes, you can, we do talk about differential invariants of curves in higher dimension and surfaces in higher dimension. The idea is essentially the same, that you have a parameterization. You hope that that parameterization itself is in some sense invariant. And then you use derivatives of that to cook up new invariants. So for example, here I used the curvature, where itself involved derivatives of the parameterization. And then I took another derivative of the curvature. So as your dimensions go higher, you may need more points. So for angles, I needed 3 points. In higher dimensions, I might need to take volumes instead of areas, right? So now, and when I'm taking volumes, on the calculus side, that somehow ends up being things like, so you can talk about the curvature of a surface, okay? But then you have to talk about curvature in which direction. So there are invariants like that, but then you have directional curvatures, and those have a similar property that all your differential invariants actually emerge from those directional curvatures. They can be higher order derivatives, but they all boil down to those curvature quantities. Does this help?
Okay, yes, ma'am, absolutely. Thank you.
Okay. Right, so this task that we are doing in a very specialized setting actually has a lot of, this is really the starting story. And again, in the last sort of segment of this talk, I want to focus on, look, we just talked about differential invariance. You just asked me this question, how much of this goes through in higher dimensions? And my answer was that yes, You just have to keep playing this trick over and over again. And if you take sufficient number of derivatives, you get a pretty good idea of what your object looks like. Now, from the point of view of the problem we started with, right? I claim to be able to say something about jigsaw puzzles and medical imaging and things like that. It's very, I mean, anytime I say shape, most of you would be thinking of shapes that have corners. Somebody earlier asked me, would I always get pi if I did that procedure of taking the angle? So all of this is bringing me to this fact that we cannot avoid, is that what happens if you have a corner, right? So if I look at a square, and there is a certain theme, there is a certain point I want to make over here. So now if I take a square instead, and I do this procedure of computing its this thing that we talked about, curvature. So let's call this P. Let's take A and B here. Let's take delta. And then what is this? So this is a little exercise for you to think about. I just lost electricity. Can you still hear me? I just want to make sure that I'm still connected.
Yes, ma'am. Yes, we
Yes, ma'am. Yes.
So hopefully my internet will not be connected. All right. So what will happen is that this kappa quantity that I have defined earlier for you for this square, so gamma is now my square, this is not going to be well defined, because what's happening is that you have an angle pi over 2, right? That was my, so how did I do this? Let me think about this. So let me see what is the most efficient way of doing this. Okay, so maybe the most efficient way of doing this is that if I look at, so I have delta over here, I have square root 2 of over here. And okay, so basically, I mean, rather than waste your time actually computing this, you're going to see that this is going to be limit delta going to 0, 1 over some power of delta. Okay, you can compute this by hand, and this is not going to be well defined. So let's say alpha is positive. So if I look at this curve, I'm not using the definition by derivatives. Of course, that doesn't make sense at this point. I'm trying to use the definition that I cooked up. And even that definition is failing. And if you look at the graph of the curvature, there are these blow up points, right? Okay, so let me kind of try to get to the crux of the matter without wasting your time. So you're going to get this. And you could say that, okay, this is also useful information, because wherever it blows up, I can say there is a corner at least. But the problem is that you can't say much more. You can't say what the angle is, whether it's a cusp or a corner. If you take something which is four-sided with different angles, you would still see a picture like this. So from the point of view of applications, this is not useful, because even if your underlying curves are smooth, when you transmit data, you can introduce certain noise. So on the receiving end, certain corners may still appear in your images. And if corners appear in your images, and when your computer is doing these computations, if it runs into these kind of troubles, then this is not a good thing, right? It's going to have problems at these corners, which will inevitably occur. So the big punchline over here is that differentiation is very sensitive to corners, too sensitive to corners. And the crux of the matter is that integration is not. So even though differential invariants, we have a complete theory, we have a complete characterization, it's only really for nice curves. And from the point of view of applications, people have moved on, in more recent times, they have moved on to what are known as integral invariants, where they want to rely on integration rather than differentiation to tackle this matter of corners. And so let me just end this with a definition of an integral invariant. So you may wonder what these invariants are. Once again, I take a curve of this kind. Of course, I can take a corner as well. That's what I'm allowing myself. Let's say I have a concept of an inside. So this is a border of a shape. So I have an inside and an outside. And what I do standing at P, so I take some radius, and at P, I look at the following ball. So I look at the ball of radius R. centered at P. And I look at the area that is captured inside. So I call this area BPR. Let's say the shape is called S, intersect S. And I normalize it by the full area of the ball. And there is something called signature, so circular area signature. So relatively new object, circular area signature, where people look at the following. They look at limit as this R goes to 0 of this quantity, this ratio. Okay. And what will happen is that at corners, so let's briefly discuss what happens. You get the angles. This is not hard to check, right? If you take a square and if I take a circle of radius R, so let me be more precise. So here, if I have a square over here, then what is my TRP going to be? So TRP is going to be exactly one quarter. I'm getting 1/4 of the circle inside. So at corners, you'll basically get angle divided by pi. That's what you're going to get. At smooth points, now this is going to sound again disappointing like before, and this is back to the question somebody had asked me. At smooth points, you will get angle, okay, let me be. So at smooth points, you're actually going to get a half over here. Okay. And this is disappointing because it doesn't differentiate one smooth point from another. What is the point of this? And the point is, again, in calculus, we should not only focus on what's happening after you take limits. So here's a fact I want to kind of talk about, maybe end this discussion with, is that actually, if you don't take the limit all the way, but try to think of this in terms of some sort of an expansion, then something is hidden over here in that, yes, it is half when R goes to 0, but it goes to half at a certain rate, and that rate involves, of course, the radius of that ball, but also the curvature of that point and higher order terms. Let's just say higher order terms. So the point is that using this integral invariant, first of all, we can work with corners. Things don't go crazy at corners. Secondly, at smooth points, a priori, it is disappointing. But from this information, we can extract the curvature, the previous quantity that we were interested in, that can be extracted from this new nice curvature, which people have studied in more recent, in applications especially. So the punchline is that maybe moving from differentiation to integration allows us certain flexibility. And the key thing is that, of course, what I haven't told you is, will the circular area signature completely determine a curve? So this also you can view as a function on the curve, because for each point you have a quantity. And the answer is that we don't have complete answers. We still don't fully understand whether there are partial results, but we don't understand whether if you give me the full circular area signature of a curve, can I completely reconstruct the curve, or whether there does even exist a unique curve corresponding to the circular area signature. Okay, so I think that, so this is, I did want to talk a little bit about, what would we even start with in affine geometry, but let me leave that as an exercise. If you, have any other questions, this would be a good time to ask. Otherwise, thank you for your attention. So I had a little update on what our friends were up to, and let's see if I can pull up the update. All right, thank you.
Thank you, ma'am. So ma'am, there's another thing. So like while we can have shapes when they're very complicated, and we would like to break them in smaller components. Mm-hmm. So if we look at all the properties which you said now, so can we carry over them as a union of all these sets, or does some properties get lost while taking union or intersection?
Good. So yes. So first of all, when you say complicated shapes, my understanding is that you may have self-intersection, for example. Probably that's what you're thinking about.
Yeah, ma'am. They can have self-intersection, or maybe they can have 3 or 4 other shapes, simple shapes, but they are intervened into themselves.
Right. So yes. So of course that
intermingling, so this is delicate matter. So even with curvature, when I'm talking about curvature, I really do focus, even if I focus on a piece. So I think I can still think about this in terms of intersections, where maybe I need to keep track of how they're intersecting and separate the intersecting curves. But maybe I'm not really fully understanding your other picture where there is some interaction between the curves. So can you maybe explain that a little bit better?
So like I'm saying, maybe like say you have a square and you have a like maybe I can put a triangle on that one of sides, and then maybe put some circles over it, and then maybe another rectangle or another hexagon. Like I'm saying that we can compute the properties of that simple objects, but as a whole it may become complicated.
Correct. So right. So as long as I'm tracing one curve, so it could happen that I merge a square and a triangle. But
Right.
if I'm sticking to one curve, if I still trace one boundary, these quantities I'm talking about, they're really local. So
Yes.
far away, you may have a circle that is not going to affect locally what is happening. That's the advantage of taking limits, and that's the advantage on focusing on the local aspects of the question.
Okay.
So yes, you can merge. One is not doing this at a global level to take unions or things like that.
Okay.
Thank you.
Yet another question. So we saw curves, and one of the properties which we can talk about curves is their curvature, which we have discussed.
Yes.
But one more thing which we can imagine is something, the notion of the length of a curve.
Correct.
So once again, so can we talk about something, once again, this is more of a generalization. So once again, can we talk about areas restricted, and what else can we talk about in a curve? Like in a layman's term, what else can we talk about a curve?
Right. So, so we did talk, you're right. We talked about lengths. We said something about curvature. Maybe if it is bounding some sort of a shape, we can talk about the area. This is a good question, right? So if you're just observing a curve and you want to say certain things about the shape, my claim is that mathematically these are somehow, there is a theory that tells you that these objects that you're trying to associate, they're all going to be combinations of lengths and curvature in some sense. They all can be written as combinations of these basic invariants we started with. So I don't know if you will have some new adjectives to describe them, but if you want to write them mathematically, there will be some either combination or higher order derivatives of them. At least for planar curves.
Okay.
So if any one of you have any other question, maybe you can ask now, or like if you have other questions after the talk, you can mail us and we will take up with the professor. So thank you, ma'am. Thank you for your this wonderful talk. Like we started from simple pictures and took us to like this. Like it was really good, and it was quite also interesting. People liked it. So yeah, we have also received comments in the comment section where people wanted to attend the talk for more time, but they had some other commitments, so they have to leave.
No problem. I mean, it's a Sunday, so you should feel free to do what you want to do. No problem. But thank you so much for having me. I really enjoyed this, and good luck with the rest of the program.
Thank you, ma'am.
Thank you.
Thank you, ma'am. So we will meet in our next lecture, which will be on 11th November by Professor Meena Mahajan on queer complexity. So hope you all enjoyed our next. Thank you, ma'am. Thank you for your time.
Thank you very much, ma'am.
Thank you. Thank you. Bye.